All right, let's go ahead and go over the questions from exam 3. So 4 questions. First one, we're looking at a related rates program problem. So, like I've said in other videos, other solution videos, it's usually best to draw some kind of situation here. So I have a ladder leaning against the side of a house, which I will assume is a right angle if I can draw such a thing. Okay. Okay, so we have a ladder leaning against the side of the house. So we will not use the Pythagorean theorem. So at the time when the ladder is 3 meters away from the house, the angle the ladder makes with the ground is decreasing at a rate of what? Okay, so we're told to consider what angle? Looks like this one here, called theta. So let's take catalog one of our variables here. Theta is the measure of angle between ladder and ground. And we're going to measure that in radians. All right. So what other information are we being told here? So we know that how long the ladder is. I'll label this side as 5 meters. The ladder is not going to change in length, so we can label that as a constant. The bottom of the ladder is sliding away from the wall. So that tells me, since we're given that rate, that means we're probably going to have to consider that distance. So let's call that, it's a horizontal distance. Is there any reason we need to consider the vertical length? So basically the height of the ladder from the base of the wall. At the time the ladder is 3 meters away from the house, the angle the ladder makes with the ground. Okay, so I don't think there's any reason we need to consider that. So it looks like we want to know something about this angle. In fact, that is the rate we want, is d theta dt. So I'll make a note of that. D theta dt is our goal. So what sides are we going to consider? So we know the hypotenuse here is going to be at 5 meters, which is constant. And we know we're given some idea of what the rate looks like, the rate of change of this distance x. So x is the distance from base of ladder to the wall. And what's our length unit? That is meters. So I think we need a trig function that relates the adjacent side of a triangle to the hypotenuse of a triangle. So I believe we're going to need cosine theta is equal to adjacent x over 5. Let's go ahead and clear fractions. That gives us x equals 5 cosine theta. So from here, what do we do? So we want to find d theta dt, which means we need to differentiate both sides of this equation with respect to time. So the derivative with respect to time of x equals the derivative with respect to time of 5 cosine theta. So that gives us dx dt equals, so we got a chain rule application here. Before I differentiate 5 cosine theta with respect to time directly, I need to differentiate it with respect to theta. So that gives me negative 5 sine theta times d theta dt. All right, so I have the rest of this information. So I want d theta dt. So I know dx dt. So I'm told that the ladder is sliding away from the house at 1 meter per second. So I'm going to call that positive 1 meter per second, because if it's sliding away from the house, that distance x is getting larger. What is the sine of theta here? So we don't know that. I mean, we could find a value of theta. I'm actually going to find sine of theta without actually trying to solve for the angle. because here's what we know at the instant we care about. The ladder is 3 meters away from the house, and we know that the ladder is 5 meters long. So the hypotenuse of this triangle is 5 meters. Pythagorean theorem will give us that this vertical length is 4 meters. So if these are the lengths of my of the sides in my triangle, then what is the sine of theta? The sine of theta will be opposite over hypotenuse, which in this case is 4/5. So 1 meter per second equals -5 times 4/5 times d theta dt. -5 times 4/5 is -4 d theta dt. So if I solve for d theta dt, what do I get? D theta dt is equal to -1/4 radians per second. All right, moving on to question 2. Blowing up balloons. We're assuming this is a spherical balloon. So we're trying to record how much a radius of a balloon, like how that increases. Okay, as I blow air into it about 1 inch per second. At what rate is the air being blown in the balloon when the radius is 3 inches? So we're given some sphere equations here. So what are some things we can identify first? So I'm going to start keying in on rates here. So I see 1/2 inch per second. So let's actually go with the sphere equations. I think these are a good identifiers of what variables I'll be using. So I'm assuming that these balloons are spherical. So R stands for radius of a balloon. And what unit am I being given for this? This is an inch. I'm also going to talk about the volume. So the volume of a balloon, that'll be cubic inches. Is there anything else I need to worry about? I'm given the formula for surface area, but now's a good time to maybe think about what we're going to be asked to solve for. At what rate is the air being blown into the balloon? So I want a rate, but what specific rate is that? So the air being blown into the balloon, I believe that's going to be dV/dt. Because if we're talking about the air in the balloon, that's going to be the space that the balloon takes up, like the whole balloon, not just the area of the outside surface of the balloon. So I believe dV/dt is the quantity I'm going to be going at. So I know something about the volume and how it relates to the radius. So I think I'm going to take this sphere equation, this first one, and relate that, or differentiate that with respect to time. So the derivative of v with respect to time equals the derivative of really 4/3 pi r cubed is also the volume. So I'm going to differentiate the volume with respect to time expressed in these two different ways. So I get dV/dt equals, first I'm going to differentiate this expression with respect to r. So that will become 4 pi r squared, and then times the derivative of r with respect to time. So 4 pi r squared dr dt. All right. So we need to know what r and dr dt are. So equals 4 pi. Do we know what r is? At what rate is the air being blown into the balloon when the radius is 3 inches? So radius is 3 inches. What is the rate of change of radius over time? I attempt to record how much the radius of a balloon appears to be increasing. Yeah, so it's about 1/2 inch per second. So 1/2 inch per second. So yeah, evaluating this should give me a value of dv/dt. So 4 times 3, 12 times a half, 6. This comes out to be 6 pi. Oh, this is not 3 inches squared. Oh, I made a terrible error, folks. This must be squared. And I just want to point out the reason I caught that is because the units I was going to get were going to be inches squared per second, which does not make sense for a volume, a rate of change of volume over time. So let's recalculate this. So it should be 3 squared, 9 times 4 is 36 times a half. So it should be 18 pi. And this time, do the units make sense? Inches cubed per second. That seems like a good unit for a rate of change of volume over time. All right, moving on to question 3. All right, so we're given this function and we want to do some analysis of it using calculus. So given this function, use calculus to determine the intervals where this function is decreasing. So how do we do that? If you want to figure out where a function is increasing or decreasing, that information comes directly from its derivative. So let's take a derivative. F prime of x equals 6x squared minus 2x minus 8. All right. If we want to find out where this thing is equal to 0, we might as well figure out where the critical points are. So let's set this thing equal to 0. I can factor out a 2. 3x squared minus x minus 4 equals 0. Divide both sides by 2. All right, so now I have this quadratic. 3x squared minus x minus 4 equals 0. Does this factor? I believe it does. So I need a number that multiplies together to give me 3 times 4, which is negative 12, and add together to give me negative 1. So I think that should be 3x. I think that should be positive 3 and negative 4. So you probably have, among the 40 some of you, there's probably at least half a dozen different ways to factor things like this. This may not be something you're familiar with, but I believe Desmos is available to you, so you can basically have lots of ways to factor this. I'm just leaning on this one because I feel the most comfortable with it. So now that I have these, I've turned my 3 terms into 4. I'm going to try to factor both, halves. So I can factor 3x out of this first one, and I get x plus 1. If I factor a negative 4 out of the second pair, I also get x plus 1, which is what I was hoping for. So I get 3x minus 4 times x plus 1 equals 0. So what does that tell me about my critical points? So I have 2 factors equals 0, so I can solve both these equations. So one of them is going to give me x equals 4/3. The other one's going to give me x equals negative 1. So I have found my critical points, which will come in handy later for one of these other parts. So to figure out where this is decreasing, let's do a sign chart. So my critical points happen at negative 1, positive 4/3. So now I need to choose test points that represent each of the 3 intervals that these 2 critical points kind of partitioned my domain into. So I'll choose negative 2. 0 is always convenient. And then what's bigger than 4/3? Let's go with 2. So I know that at x equals 1, negative 1, and x equals 4/3, I have, so values of the derivative are 0. So now we need to evaluate f prime of negative 2, which is 6 times negative 2 squared minus 2 times negative 2 minus 8. So that's equal to 6 times 4, 24, plus 4, 28 minus 8, that's 20. Positive number. So what's happening to the left here? I have increases. What about f prime of 0? Very easy to evaluate. I get negative 8, less than 0. So I think I found some values where my function's decreasing. And then finally, what happens to f prime of 2? F prime of 2 equals 6 times 2 squared minus 2 times 2 minus 8. So 24 minus 4 minus 8, that gives me 12, positive. So the only subinterval where I have decreases are in between the two critical points. So this function f decreases on -1 to 4/3. So that's the answer to part A. Moving on to part B. Really meant to resize all these. Give me a second. All right, back to it. All right, B, use calculus. Use calculus to determine whether each critical point is a minimum, maximum, or neither. Okay, so my critical points are where? X equals -1 and positive 4/3. What did I say my derivative was? 6x squared minus 2x minus 8. F prime of x equals 6x squared minus 2x minus 8. Is that correct? That's what I have. All right. Justify your answer using calculus and provide sentence explanations for each. So there are at least two ways to do this, two that we've focused a lot on. So why don't I do this? Why don't I justify one of the critical points using a first derivative test? So let's do that. We already have the first derivative test set up. So let's look at x equals -1. So I know I have a critical point at x equals -1. And I know from the sign chart here that when I have x values less than -1, my function's increasing. And for x values greater than -1, my function is decreasing. So that tells me that f has a local max at x equals -1. Now, am I asked for both coordinates or am I asked for? It's not clear. So let's do this both ways. Since it's not clear, I'm not going to hold it against you. Didn't give me y values, but I will give you y values. So at x equals 1, so that point is, let's evaluate it. F of -1 equals 2 times -1 cubed minus -1 squared minus 8 times -1, which is equal to -2 minus 1 plus 8, which is 5. So local max at -1, 5. So that's how first derivative test can be used to justify that. Let's use the second derivative test to classify the other critical point. So to do that in the second derivative, what's f double prime? That will be 12x minus 2. And I want to evaluate that second derivative at my other critical point, which we said was 4/3. So f double prime of 4/3 is equal to 12 times 4/3 minus 2, which is equal to 16 minus 2, which is equal to 14, which is a positive number. So I have a critical point on a function. So I have a point where the horizontal tangent line, or sorry, the tangent line is horizontal, but in the area, in the neighborhood around that point, the slopes are increasing. The first derivative is increasing. That means I have to have a local min at x equals 4/3. So let me get you a y coordinate there. F of 4/3 is equal to 2 times 4/3 cubed minus 4/3 squared minus 8 times 4/3. So 2 times 64 over 27 minus 16 over 9 minus 32 over 3. Let's get some common denominators. So 128 over 27 minus 48 over 27 minus 32 times 9. What's that? 30 times 9 is 270. 288 over 27. Did all that in my head, and then we're going to go to the calculator now. So 128 minus 48 minus 288. So that equals negative 208 over 27. So local max at negative 1.5, local min at 4/3, negative 208.27. Right, that's part B. And finally, part C. Use calculus to determine the location of the inflection points. Only need the x values. Okay, so what is an inflection point? An inflection point on a function is where the concavity changes, either from up to down or vice versa. So where might that happen? That might happen where the second derivative fails to exist or where it equals 0. So those are our candidates. What does our second derivative look like? We found the second derivative was 12x minus 2. So f double prime of x equals 12x minus 2. So this is linear, which means I don't think there's anywhere where we're going to make this undefined. So we're really looking for places where it equals 0. So solving this equation, I get 12x equals 2, x equals 1 over 6. Is this an inflection point? It could be. I don't know yet. So how do we find that out for sure? Sort of a very abbreviated sign chart. So this is a sign chart for f double prime. I know that at 1 over 6, my concavity, basically, it's neither concave up nor concave down. So now I want to choose values on either side of 1/6 to test. 0 and 1 are both available to me, so I'm going to use those both. What is f double prime of 0? That is equal to 12 times 0 minus 2, negative 2. So that's concave down. How about f double prime of 1? That's equal to 12 times 1 minus 2. That's equal to 10, which is concave up. So that tells me certainly that I have an inflection point. F has an inflection point at x equals 1 over 6. All right, that's all for question 3. So I have this side-by-side rectangular pen I want to build. So let's start devour, like representing the lengths of this fence in terms of, or this pen in terms of variables. I'm going to call all the horizontal members x, all the vertical sides y. So what is it that we know about this pin? The wire mesh around the outside costs $4 per foot, while the solid fence in the middle costs $10 per foot. So we're going to build a cost function, and that cost function is going to be built on lengths. So the outsides, basically, I'm going to do this. I'm going to make a point right here. I'm going to, from that top left corner, I am going to basically move around the outside of this pin in a clockwise fashion and build my function, or my objective function that way. So this first x, that's around the outside, so that's going to be $4 per foot, plus another x, that's $4 per foot, plus a y, that's $4 per foot, plus 4x, plus 4x, plus 4y. So all the lengths around the outside of this pen are going to be $4 per foot of length. but then we still have to add in the solid fence in the middle that costs $10 per foot. So that's also Y. Okay, so start collecting all these terms. How many X's do I have? 4, 8, 12, 16. So 16X plus 4, 8, 18Y. So I think this is my objective function. 16X plus 18Y for the cost. So what else what am I bound by? You know, if I wanted to minimize the cost of this thing, I would just build it as small as possible, but I want to have a total area of 300 square feet. So what's my area here? My area as a function of X and Y is equal to, it's a rectangle, so it's going to be length times width. My length is 2X and my width is Y. So, and I want this area to be equal to 300. So let's do this. Let's solve this for either X or Y. Let's go ahead and do Y. So Y is equal to 300 over 2X, or 150 over X. And now that we have that, we can write our objective function as a function of a single variable. So 16X plus 18 times 150 over Y, or 16X plus 2700 over X. So here's our objective function. We want to find a critical point for it, so we need a derivative. So C prime of X is equal to 16 minus 2700 over X squared. And to find a critical point, we got to set the derivative equal to 0. So now we got this equation, 16 equals 2700 over X squared. Multiply both sides by X squared, gives me 16X squared equals 2700, or X squared equals, a number will approximate whatever 2700 over 16 is, 168.75, which means that X is equal to, I think 169 is 13 squared, so this should be really close to 13. Yeah, 12.99. 12.99. So this is my critical value of X. Have I solved the equation? I don't think so. I think I want to know what the minimum cost is. Now that I have that critical value of X, let's go ahead and evaluate the cost function for that value. So C of 12.99 equals 16 times 12.99 minus 2700 over 12.99 squared. And let's find an approximation here. Oh, I did something. Okay, let me make sure this error didn't hurt me in more places than this. So this should be 16. But no, that's correct. Oh, don't plug things into the derivative. Come on, man. All right, let's back up. So I mixed the derivative up with the objective function. So I want to evaluate the objective function at this X value. So C of 12.99 equals 16 times 12.99 plus 2700 over 12.99. Now that we got the setup correct, it's actually approximated that. And I get a final result of $415 and 69 cents. There we go.